the surfaces of constant temperature but separated by 1 unit.
Yeah.
So okay, let me draw it. For Cartesian coordinate, it will be easy to see what dt means. So for Cartesian coordinate, say this is my xy plane, right?
Yeah.
So z equals to 1, I can draw another one. Z equals to 2, I can draw another one. So from the center, any point you go, say you go to this point and you have a coordinate x, y, z. Now, if you ask how many, what is the distance in x-axis, z-axis that I passed, that would be the piercing between that total vector and how that vector cuts this, like z equals to constant surfaces.
I did not get it. Can you tell it again?
Okay. Yeah. The way I said it was confusing, obviously. So in it, you are drawing z equals to constant planes, but that you are varying that c by 1 unit. C equals to 1, c equals to 2. That's how you are drawing this.
Okay.
So now, if you go to any arbitrary point that has a coordinate x, y, z, but or actually let's make it proper. So say you go to a point that has coordinate x naught, y naught, z naught, and you draw a vector this. So that vector must cut z naught amount of surfaces when it reaches there. Obviously, we are considering like probably we could say like number of surfaces are integer, but here z naught could be a fraction. Actually, we are considering the fractional as well, fractional portion. So if it is go to the halfway, if it end up being here, then we saying it cut the like 1.5 surfaces. That's what we mean.
Okay. Does the fractional part will have any effect on temperature?
So for the temperature, we are also considering that fractional as well, because if we ended up being here, like if this were our vector, then
yes,
the temperature between these 2 points we were considering. So that's also we are considering fractional.
Okay. But in middle space, I mean to say that between two plane there is no temperature source. So that's so I was thinking that the temperature associated with the fractional space should not be measured.
No. You did not get it then. So we are just for the sake of drawing, we are drawing few, but hypothetically there are infinitely many surfaces where
now I understand. Yes, actually there are infinite number of surfaces, and
yes.
Okay.
Here we are drawing just the integer ones that we can actually draw here. Otherwise, like how can I draw infinitely many, right?
Yes, it has been drawn for simplicity only.
Yes, it was drawn.
Now I get it.
So now dt, those are like stacks of those planes. That when you provide the vector, when you pierce it, it provides you the actual separation between temperatures. So dt has all the information anywhere you go or any direction you go, how much it will change, all the information. But when you provide the displacement vector, then you measure that how this much temperature or this much quantity was changed.
Yeah.
So this is what we mean by one forms. So now we need to develop some intuition of adding vectors and one form. So for adding vector, we have a pretty good intuition. So we always think about, like, if we add two vector, we have to mentally draw a parallelogram, and corner to corner would be the resultant vector, right? So also we have the intuition of multiplication. When you multiply this vector by 2, it becomes this, because it will have like the double amount of length, right? So how do we do the same thing for those stacks of plane? We need a mental picture of that to build intuition, right?
Can you please repeat the question?
So you have a good mental picture, like how to add two vectors and how to multiply a vector by a number.
Yes.
So when you add two vector, you just mentally you draw up parallelogram, and corner to corner distance is your new length of vector, right?
Yes.
And for scaling up a vector, you just multiply by that number. It just norm becomes that much bigger, like m times bigger. Say here I have drawn twice bigger. So how it is done for dt, or generally one form? Obviously one form can be drawn as a bunch of planes, right? So how do you add two stacks of planes? So it's better to see the diagram on the book here, because I won't be able to draw a diagram that good. So it's better to look into the picture. So could you please open your book in page 57.
Yes. It is like I taking another temperature source.
Yes, adding two, like when you are scaling up, you're just multiplying the temperature source. So what do we mean? That if say one form is like represented like this, like one stack of plane.
Yes.
If you want to multiply it by 2, then all you have to do, you have to draw more planes inside of it. Like that.
Which page of the book you said?
It's 57.
Okay.
57 shows the addition.
Okay.
Carl, are you here? Carl? Hello? I think you have connected through your mobile.
Yeah, I'm sorry. I lost the internet, so I'm on my phone, but I am here.
Yeah, it's fine. So could you please look into the book, page number 57?
I did. I see it. That's
okay,
good.
so yes.
Thank you.
So you have two stacks of planes, and when you add those, see the first one, like the alpha one. Alpha one was like all the plane was on z direction, right? All the plane had a face on the z direction. Now for the beta one, you have all the faces on y direction. So when you add those two things, the new surfaces have the face in between somewhere, and the density of the surfaces has increased. So here the density, like how much surfaces you have in unity distance, that's the measure of the norm here, length, like magnitude here. Is that clear, everyone?
Yes.
So for multiplication,
It's basically how the constant surface changes.
sorry?
It's actually how the constant surface changes.
Yes. So if you face another surface more frequently, then you have like that quantity, that temperature probably is changing really frequently, really fast, and it doesn't change that much, then like constant surfaces of unity separation will have like longer distances.
Yeah.
You have to go further to get 1 unit separation.
Yeah.
So it's just the opposite of vectors. So when you draw the vector, when you multiply that thing, you just had to double the length. Here, doubling the length doesn't mean anything. Here you have to increase the density,
Yes. Yes.
double the density.
Yeah.
Okay. Is that clear to everyone? Arafat, did you get this part?
Yes, I got this.
Okay. Let's ask everyone, because this part is really crucial and I do not want to miss anyone here. Ankon Dash,
Yes, sir.
did you get this part?
Sir, I would like to ask you something like, well, is it along the lines of the covariant part you explained earlier?
Sorry.
Well, is it like the covariant part you explained earlier with the basis and the?
No. Here, these are the full objects. Remember, changing the coordinate, they do not change themselves. But if we want to change the quantity itself, then we have to like draw it differently. Just like the vectors. Vectors itself do not change in the coordinate transformation. If you want to like double the vector, you have to make it such that it looks longer.
Yes, sir. All right then, sir.
Okay. Durjar, did you get this part?
Yeah, I got it.
Okay. Humaira,
Yes,
hmm?
yes, I think that images from the book.
If you have any confusion, please ask. Javed, did you understand?
Yes.
I'm not clear actually.
Okay. Yes, Bajaj. Yes.
Actually, I was just looking for the page and I did not listen to the. I know the initial part when we were talking about the vectors, normal vectors, but when you were talking about the book, I could not listen that thing.
Okay. So you want me to repeat it again?
If
Yeah,
you
it would be better.
So are you looking into the page number 57 of the MTW book?
yes,
So you see the figure that they have drawn two one-forms. One is alpha, another is beta.
yes,
So alpha is facing on the upward direction.
yes, I can see that figure now. Yeah.
Yes, and beta is facing on the y-axis probably.
Yeah, and adding to makes the
Yes, when you add
makes the
those things,
angle actually not
yes,
yeah.
you have a new stack of surfaces, but they are now pointing in YZ direction.
Oh, okay.
So
Yeah, I
yeah,
what I understood that it is not like a normal addition of vectors.
yes, it's not like normal addition. Yes. Also, if you want to multiply by 2, say, if you want to multiply by one form by 2, you do not you do not add more surfaces on top of each other. You just add more surfaces in between.
Yeah.
So is that clear to everyone?
Yeah, kind of. Yeah.
Okay. I think Humaira was trying to ask something.
Actually, I didn't get the why it's tilted.
The last one, the last surface.
Yes, yes.
Yeah. So let's do it algebraically. So the first one, say alpha, is dz basically. So you are trying to draw surfaces that are parallel to XY plane like this. And when you have like beta, say dy, let's write 2 dy. So if I write 2 dy, then this is my 1. This is y equals to 1, y equals to 2. So as I have 2 dy, I have to write, like, to get 1 unit separation, I just go here. So I have to draw these surfaces. So this will be one of my surface. Then this will be one of my surface. This will be one of my surface. You see the density is doubled, like it's more frequent than previously. But when you add those two things, so when you do alpha plus beta, so then dz plus 2 dy. So it'll be tilted. It'll be tilted in yz direction, right? And as y has more magnitude, it will be more tilted on y direction than z. So it'll face like this way. So I have to draw planes like this, and with a higher frequency actually, because the magnitude has changed like that. I'm bad at drawing, so please try to understand. So you could think adding areas. So if you think about area vectors, so area vector, like it was this direction, this was this direction. So you add those two things, it will be like this direction. Or you could think about other way. If you project this alpha plus beta on two part, so the projection on z direction would be like this one, and projection on y part would be like this one. Is that clear?
Yeah.
Okay.
It's clear, but in the book, what is that positive sense?
Oh, positive sense. Vector, for vectors, we had a predefined positive sense, right? Because we always write as arrow, and that arrowhead that tells which direction to which direction I have to go, right?
Yeah.
But when you draw this kind of a stack of plane, you're not sure, are you going this way as positive or this way as positive? So typically you draw a dot 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 vector to say that this way actually my positive way. Like which way the change is positive. You could actually like do the same thing in other way. Like on the top surface, probably you could put a dot over there. So that's the highest value of the surfaces. That will understand that actually we are going this way. And if you do not draw that dot, we'll understand that it's going opposite way.
Okay.
So it's just the convention. Okay, so now we have an understanding of three things: vectors, what we understand by vector, what we understand by one form, and what are the piercing mean, right? What do the piercings mean? Okay, so let's try to do few piercings. That will be great, right?
Can we call that piercing is a generalization of inner product or something like that?
No. Inner product is basically the dot product, right?
Yeah.
Inner product is
Or more general thing.
the same vector.
Actually, it's hard to tell which one is generalization of what.
Yeah.
Just let me tell. So yeah, it's a kind of generalization in the sense that
Bhai, can you hear me?
yes,
In Pearson, we take object from two different vector space, but in inner product we take object from the same vector space.
Yes, yes.
So
So that's not even generalization. So okay, okay.
Oh, yeah.
Inner product.
I got
When
it.
you call inner product, it's A dot B, right? So inner product from now on, we are going to call it this thing. This is going to be our inner product. Inner product of AB is this. But the piercing is also the same thing, except for if you keep the B as same, but you have to change your A into the corresponding one form, say alpha, and do this. So to change that, your alpha has a definition now, ds square on A.
Yeah.
So in a way you could say it's a generalization, in a way you could say no, those are two different things. So when I'm just talking about Cartesian coordinate, I'll say, okay, yes, this is a generalization of inner product. When I'm talking about arbitrary coordinate, where may not that ds square exist at all, then I'd say this one is actually like this one is actually more general, because what you say, yeah, no, sorry, this one is actually generalized. Yeah, so because even when you do not have ds square, you still, if you have one form and another b, another vector, one form and vector, you can always do the piercing.
Yeah.
Remember, it doesn't matter how much distance, what is the notion of distance over there, like let's say PV diagram. Let's draw the PV diagram. Okay, so this is my pressure and this is my volume. So I do not know what's the distance between these 2 points. It's not
What
even
does it
defined.
even mean?
It means something. It means something. This vector means you had an initial state like P naught V naught, then you went to another state like P1 V1. It means something.
Okay.
So this arrow means a change of state, and that's meaningful. So vector is defined, obviously. We can define vector between 2 points, that's fine, but we cannot define the length of that vector. Also, we can define one forms, say like change of pressure. So on PV diagram, say these are my constant pressure surfaces.
yes.
And you still have that piercing, like when you go from this point to that point, you still cut 2 surfaces of pressure. So that piercing is 2, but you do not have a definition of length defined here.
Yeah.
So in that sense, piercing is more general.
Yes.
Okay, but it's not an inner product. Remember, for inner product, we take a product between 2 same objects. Here, piercing is done between 2 different objects. Inner products can be written as piercing, but the converse is not true. So let's define few conventions. So if you have,
Can we get a break?
just give me a few minutes. So let's say you have a vector. Now you have a corresponding one form. Let's call it V lower bar. You do this using metric tensor ds squared. We call it flatting. So flat of V which is defined as you have to take your metric tensor, supply one of your in one slot your vector and leave another slot empty. That will give you V lower bar. That's the definition. So that's how you change from your vector to one corresponding one form. So to convert your vector to a corresponding one form, you must have this ds square. So we'll see later that if you have a ds square defined, we'll have the corresponding inversing metric tensor defined, that is G. And G, what G does is it can change up one form. If you have a one form, you can change the corresponding thing. Say let's call it differently. Let's call it one form alpha. You convert it into a vector, and that is done by G upper bar. So all you have to do, it's written as like this: sharp of alpha. If you sharp a one form, you have to do like, you have to take a G upper bar, that's basically inverse of this metric tensor. So leave one slot empty, in another slot supply that alpha, and then you'll get alpha upper bar. So we'll talk about this thing later. Okay, let's take a break. But before going to break, just remember one thing, that this ds square, if ds square is defined, then G bar is defined. But if it is not, then G bar is not even defined, and you cannot convert a one form to a vector to one form. And finally, we can convert our momentum to a vector because in Cartesian coordinate in flat space we have definition of ds square. That's why we have a correspondence between vector and one form momentum. So, but otherwise we do not. Okay, let's take a break. 5 minutes. Okay, next day we'll actually learn the formal definitions, starting from how to construct tensors, and then this thing, like the thing we talked earlier, will be clear. It takes some time to get comfortable, because you remember, like, you had your vector calculus courses, and it took a while to understand and to get comfortable with the algebra and calculus stuff. So the same thing here as well. It takes some time, but when you're comfortable, then it's pretty straightforward. Do you have any question, guys? Hello? Hello? Is there anyone here? Yeah, Prashanta is there.
I'm here.
Anyone else?
Yes, I'm here.
So if you guys have any question, you can ask in this break. So it's 4 minutes already. We'll have 1 more minute. Let's not waste another day. Do it today. Like I was talking about teaching the formal stuff. Like starting the formal stuff actually. A little bit more formal stuff. Yeah, we have time. I think I can do that. I'll give you some example of this vector and one form, then we'll start.
So in this, we'll be always considering, along with the vector, we'll be considering the surfaces
Yes,
also?
yes.
All. Okay.
Not surfaces, those are called one form. Or two vectors.
One form. Okay.
Okay, let's get started again.
Can you hear me?
Yes, I can hear you. Yes.
Why the name is one form?
Because we have a general definition of arbitrary P form. We'll see that.
I think one differential, first order differential form, no?
Yes, yes. First, like these are DFs are one forms.
Yeah.
For what I'm writing. Forms. Yeah. So we have an arbitrary general definition of P form. We'll also have a general definition of Q form as well. Q vectors or P vectors. P vector. So the ordinary vector we are talking, you could call like one vector. You could call it as one vector. Or the same way, like you could call one form to be co-vector as well.
Is there any similarity with LP space or?
Sorry, similarity between? Similarity between?
LP space.
What is LP space?
Oh,
I do not know. What's that?
L2 space is Hilbert space and something like that. Actually.
Oh, L2.
Yeah.
You're talking about L2. That's what you mean.
Yeah, LP space. Is there any similarity between LP space or P form?
Yes, Hilbert space. Hilbert space has the same linearity structure for functions. So you call a function like this. These are your vectors basically, but infinite dimensional vector.
Yeah.
And when you because Hilbert space has a metric that is diagonally one, basically this thing x minus x prime. This is your component of metric tensor in Hilbert space basically. So this thing, the corresponding you could call it one form or we call their bra, right? Here we call it. So it's defined to be integration of a slot. Then what? Then the vector function, the thing dx, like that. I believe it's correct. So here it can take a vector, right? Or a function basically. You can take a function over here and perform it. So this object is an operation. It's itself is nothing. It's an operation. It acts on some function, say f. So when you act on something, here you have to write that f over there, like that. Here also one form has the correspondence. So k's are basically here vectors. So this v. And one forms are alpha, like that. But here alpha itself has geometric meaning. That this bras they lack. Probably, yeah, you can define it and have a meaning as well. Okay. Let me give you some example, because then it will be clear that what we are doing. So you know what the momentum is, right? Say momentum in polar coordinate. So how did you define the corresponding momentum in polar coordinate, like consistently for each of the coordinates? So we had a Lagrangian, remember? And we had half m, then r dot squared in polar, written in polar coordinate, plus r squared, theta dot squared plus r squared sine squared theta, phi dot squared.
Yes.
Then pr, the momentum had a like r component of momentum was defined by delta L over
delta r dot.
Yes, m r dot. Great. And p theta was defined as delta L by delta theta dot, which is
mr square
theta dot. Yes, and then p phi, it was like delta L by delta
mr square sin square theta phi dot.
Okay, now if we consider the velocity in polar coordinate, what did you get? Velocity in polar coordinate, r dot er, is that correct?
Yeah.
Then plus
R theta dot
e theta.
Yeah.
I want to write this way.
Okay.
And phi dot e phi, like that, right? So now if you want your momentum to be vector like this one, so you could define your p vector to be like m multiplied by v vector, and then it would have a component like p r, say it would be like m r dot. That's fine, just substitute, right? But p theta would be like m theta dot. So you're missing this portion, right?
Yeah.
P phi equals to m phi dot. So you can see, like, we could define this way, but this is not a very straightforward natural definition.
Well, we can define this if you use orthonormal basis, I think.
Sorry?
For orthonormal basis.
These are orthonormal basis. These are not. Oh, these are not normal. Yeah, these are not normal. These are orthogonal basis. Okay, but that won't be natural. That won't be natural, because when you take dot, like L has to be in this form, whatever you do, right?
Yeah.
So natural definition in L will always be like this.
And these are the component of orthonormal basis, I think.
These are the component
of orthonormal basis also.
No.
Square of the components.
No. So what's true definition? Let's see. As I said, momentum is basically one form in its like natural way. So the true definition of momentum would be like this: mass multiplied by velocity but a lower bar, which means you have to flat your velocity. That's the true definition. Sorry. You have to flatten your velocity, which means you have to multiply by the metric tensor. Like you have to do this. This is the true definition.
Okay.
And you see it will work because your ds square, you remember, ds square was what? 1 in polar coordinate. Remember, in spherical polar coordinate, it was like 1 0 0 0 r square 0 0 0 r square sine square theta.
Yeah.
Now, if you multiply by this r dot theta dot phi dot, then you'll get this r dot, then r square theta dot, and then r square sine square theta phi dot. And then if you multiply by that thing m, you'll get the correct form. So does it seem more natural to you now?
Yeah.
Yeah.
Yes, there is another thing we need to know, that remember, to have a relation between velocity and momentum, it was necessary to have a definition of metric tensor, right? Metric. So basically, you cannot do mechanics. You cannot do mechanics when you do not have a definition of metric tensor. You need a metric to do mechanics, because otherwise the distance is not defined. But in mechanics, like the distance is like inherently there. Okay, so we saw one example. We could see more, but if you are happy enough at this stage, I think we should proceed. And because we are going to do a lot of stuff with this, it will be clear eventually. So let's not waste more time on it.
Okay.
Okay.
Okay, so is this part clear to everyone? Carl, did you get this part? Okay, so
Yes, I did. Thank you.
okay, great. Bajaj?
Yeah, just one thing, like this empty slot which we have, p is equals to m into v, then we wrote m ds square bracket v vector comma. Previously also we had this empty slot, but I could not get why we have this.
Because this whole object, this whole thing can take another vector inside of it.
The whole thing?
Yes, this ds square can take another vector over there. So you could say like, I want my momentum and the piercing of velocity. You want that. That's a real scalar. Scalar. So obviously that will give you mv square here. Like then you have like a v over there, like p dot v. Not p dot v, like p pierced with v. So it's basically m v dot v. So that thing still can take another vector. So just remember, when you write a vector, some v, it can take one form and produce a number. Usually you could write like this, like mathematician would like it this way. So it could take a one form and produce a number. And when you have on one form, it also have a slot. It can take a vector and produce a number. And those are actually same thing. So this whole thing, like ds square, it were able to take two vectors, some a and some b. So if you do not provide the second vector, just provide the first one, it produces a one form, and that's the corresponding one form of a.
Okay. And if both are present, then
you get a number.
Then we okay, yes, got
like
it.
When both are present, then you just get this thing.
Yeah,
like,
If we give the one form, then we get the.
So yes, so for ds square, it can take only vectors in two slots. ds square, you cannot provide a one form over there. No, like you cannot do that. No. But ds square has a corresponding tensor, that is G, that can take two one form, like alpha and beta, and that will again produce a number. So that thing will be used to convert a one form into vector. So we'll see this thing in full detail. Let's proceed.
Yeah.
It will take a little bit more time, I think.
Yeah, sure.
We have 20 minutes left. Okay, so forget about everything. Just remember two things. We have two kind of object. So far we have learned vectors and one forms. Is that clear to everyone? Just two kind of object, and
Yeah.
forget about metric tensor and all that, because we haven't defined tensor yet formally. So, okay, we haven't defined tensor formally yet, but we are going to. So these two objects, they can perform several operations to produce new objects or new tensors. So one we already learned. Another is we can perform a piercing between those two. This thing, which is geometrically speaking, that piercing the stacks of alpha, piercing constant surfaces of alpha, integral of alpha, and then like constant surfaces of not constant surfaces, like stacks of alpha or surfaces of alpha, and you pierce V, you get a number. That number is already, we know, like alpha mu V mu, that's the number. Okay, so we were able to, we had two things. We had like scalars, a vector, or one vector, let's say, and we have one form. Using these two things, this one, that one, we can produce more type of vectors, more type of tensors. Now we are going to define a tensor more generally. So mathematically speaking, a tensor is an object. Tensor is generally an object that have many slots that can either take vectors or one form in it, and when you fill up all the slot, it gives you a number. That's a tensor is. Coordinate independent number. It doesn't depend, the result, final result doesn't depend on.
Can you please repeat the last sentence?
So definition is, T is an object. T is a geometric object like vector and one form was. T can take as many vector if necessary, like probably 2, 3, 4, 5 it will take, and probably it will take, like, it depends on how many slots it has and which slot can take what. So let's give a specific example. So say you have a vector v uvw. Let's say you have a vector uvw, 3 vectors, and you have 3 one forms, let's say alpha, beta, and gamma. Now you could have a tensor that can take in its first slot, say it could take a vector, then its second slot it could take a one form, third slot it could take probably another vector, fourth slot it could take another vector, and fifth slot, and probably that's the last one, it could take a one form. So this
Yeah.
And when you, yes, when you provide all,
Yes, serial matters.
yes, here serial matters. Yes,
It's basically tensor product between dual space and the vector space.
So T, what T is, we'll see later. So that's the definition of T. We'll expand it. We'll know more detail about it. So T is an operator that takes vector and one form and produces a number. So it, like, type of T, what kind of T is that? It depends. What kind of tensor is that? It depends how many vector it can take and how many one form it can take, and particularly which slot it can take what. So yes, the order matters. So this T, as I said, first slot it takes vector, second slot it takes one form. So in this slot, you cannot provide a vector. No, that's not allowed. This slot, you cannot provide an one form. That's not allowed. So the slots are well defined, what you can provide. And finally, it has, when all the slots are taken, it should produce a real number. So why we define this way? Because you see, this way it becomes geometric, because vector is a geometric object, one form is a geometric object. And T takes vector and one forms and produces a number which is independent of coordinate, then T
Well,
must be a geometric object.
can we say that dot product is a tensor then, or
Yes, that's the metric tensor. Dot product is basically a metric tensor that can
oh,
two
okay,
vectors a number.
Yeah.
Okay, so we already have a seen two kind of tensor actually. Another is, one is a stress tensor. Probably we have learned it. Force per unit area is the stress.
Yes.
Let's call it S probably, or probably it's denoted as T.
Or inertia tensor.
So, or yes, better, inertia tensor, moment of inertia tensor.
Yeah.
Inertia tensor is a tensor that acts like a mass, right? It can take two vectors in its two slots. It has two slots. It can take one vector that is omega, the velocity, another is also omega, and it produces a number. We have seen metric tensor, ds square. It takes two vectors and produces, a dot b. So it produces basically a dot b, which is a number and independent of coordinate.
Yes.
Okay, so now how to construct this T, that we haven't seen yet. Let's go there. Okay, so vector, like constructing a higher rank tensor. Okay, before constructing, let's define few terminologies that will be helpful. So type of tensor. So tensor is called a zero tensor, or more precisely a zero tensor. If it cannot take a vector or a one form, it's already a number. So basically these are scalars.
Yes.
These are scalars that cannot take any vector or any one form. That's already number. So yeah, these are scalars. Zero tensors. Okay, 1-0 tensors.
Oh,
Any guess
one
what it
vector.
was?
One vector.
Yes, these are vectors basically. These can take one form.
Yes.
They can take one form. So the first slot says how many one form it can take, or how many vector order does it have. It has one vector order, so it's just vector. Then
what is rank? Is the rank is the number of vector it can take? What is rank of a tensor? Is rank
rank of a tensor the total sum of the vector and one form it can take.
Yeah. Then it is one form.
So these two are both first rank tensors.
Yes. It is one form.
So one tensor, what's that?
One form.
These are one forms, right? These are one forms. Why? Because it cannot take any vector in it, but it can take. What did I say? No. Sorry. It can take one vector in it, but it cannot take any one form in it.
Yeah.
So yes, those are. Okay, so can you tell me what are those metric tensor are like ds square? What kind of objects are they?
This is 2 0. Oh,
Is it
sorry,
20 or 02?
sorry, 0 2.
I think 02.
These are
0
02. Why?
Yeah.
These are 02 because it
Second
can
vector.
take. Hmm?
It takes
It can
two
take.
vectors.
It takes two vectors, right? That's why it's 02.
Yeah.
What are those G bar that can take 2 alpha?
It's 2 0 tensor.
It's 2 0 tensor, right?
Yeah.
And like that, you get the idea, right? So typically, you could have a tensor that can take m number of vectors and n number of one form. So that we call mn tensor in general.
Yeah. Rank is m plus n.
Rank is m plus n, right? Okay. Is that idea clear? Like type of tensor?
Well, if the rank is like n, and we can have a many type of tuple, I think, because this
Yes,
this
yes. So
yeah.
for mn tensor, for m plus n tensor, you could have many. Like this is not a specific kind of tensor because it could have many combination. Like
Even it can
this.
have 3 slots or 4 slots.
Yes, yes, yes. So like yeah, say 20 tensor, like second rank tensor. How many possible second rank tensor can we write? So second rank tensor can be like some t that can take by lower bar, I mean it can take a vector. By upper bar, I mean it can take a one form. So yes,
It's basically
so
permutation.
it can be this. It can be this as well.
A permutation with repetition.
Yes, all possible permutation actually. This is the second rank tensor.
Yeah.
So this tensor probably will have a type. It has a type like it can take two vectors. So it's a 20 tensor, right? The first one, like it can take two vectors, so it's a 20 tensor. So that last one, it can take two one forms, so it's a 02 tensor.
Yeah. Well,
And
I have a question. What is Kronecker delta?
Huh?
What is Kronecker delta then?
It's hard to answer, but we'll know. Kronecker delta can be a scalar, can be a vector, and
Yeah.
can be a second rank tensor.
It is 1 1 because we saw last time that the dot product between the basis of dual space and the vector space will produce conical vector.
Yes. So with that definition, we have like Kronecker delta to be a scalar, right?
Yes.
But
Yeah.
I could write like I have a vector that's e mu, the basis vector itself, and I could write delta mu nu e nu. So now Kronecker deltas are component of a vector. So it could be vector. And it could be a 1-1 tensor as well. So say you have an identity matrix or identity tensor that is omega mu Kronecker delta mu nu e nu. So it's a second rank tensor. So it depends how you want to use your Kronecker delta. It depends on the very definition of Kronecker delta.
Yeah.
But the Kronecker delta doesn't take any vector or one form.
Kronecker delta itself is a number. This is a number. So itself is not a vector or anything. It's just a number. But that number could be a scalar. That number could be a component of a vector. That number could be a component of a second rank tensor.
But can it take any vector or one form? like
Nope.
the definition of tensor.
Nope.
So in that case, how can
So this object can take a vector itself. This object can one vector one form in it. So I do not get, where did you get confused? As I said, it's a component of a vector, component of a tensor, not itself a tensor, not itself a vector.
Okay, then there is no problem.
Actually, this confusion arises from the matrix representation as well.
Yes, so we should not do that again. Like usually we represent it as matrix when we learn it in elementary level, but Kronecker delta is a number only. It doesn't have, it's not a big object. It doesn't have any thing, like it could be a component of a big object, like as I have shown, like it could be a component of a vector, it could be a component of a second rank tensor, that's fine, but
it's not
the
second rank tensor.
So it depends how you define your like how this Kronecker delta arised, in which context did it arise, that it matters. So it could be a component of a vector, component of a tensor, or it could be purely scalar. So okay, so now these two tensors, as I was trying to show, that the first slot it takes one form, second slot it takes vector, and the opposite it takes. So these both tensors are known as 1-1 tensor. So it's kind of confusing. Obviously, those are not same thing; those are different. But those are named as 1-1 tensor.
Those are same type of tensor. Can you say that?
Yes. Same type of tensor. By the way we have defined our type.
Yeah, obviously.
So the type doesn't directly say what it is, or which slot can it take what.
Yeah.
So we have to be careful when dealing with this kind of situation. We have to be careful about which slot can take what. So I think the definition of tensor is clear for this session at least.
But is it unlike the two distinct different vectors? They are not same thing, but same type of thing. They are vectors, but two different vectors. So they are two different tensors, but 1-1 tensors.
Sorry, I did not get it.
I mean, if I have two vectors, but two different vectors, they are same type of tensor, but two different tensor. Here also, can I say that they both of them are 1-1 tensor, same type of tensor, but two different tensor?
The definition, the distinction is much more than that. So a 1-0 tensor, cannot be any other type. Like it has only kind of tensor that is 1-0. There are only one kind of tensor that is 1-0 tensor.
Yeah.
It's just a vector. But a 1-1 tensor can be a tensor that takes a one form, then a vector, or it could take a vector, then a one form.
That means a 1-1 tensor also two types of tensors.
Yes. 1-1 tensor are two types of tensors combined in a single package. So we have to be careful. Like the definitions are not that clear. The clarification comes from what we have written over there. Okay, I do not have much time today anymore, so I should not extend this lecture, but I think the next day, the first thing we should discuss is about there are 8 possible ways you can construct a tensor out of vector and one form, out of elementary vector and elementary one form. So we should learn those formally. So that's the biggest step of learning tensor algebra. So when you learn that properly and able to manipulate things, then it will be easier. Then we'll come back and reconcile some concepts.
Okay.
Okay, any other questions so far?
No.
Yeah.
Okay.
Components of tensors are always numbers. aren't they?
Yes. Yes.
So if Kronecker data is a number, so why we should call it a component of tensor? It's just scalar, isn't it? Like
No.
real numbers.
Scalars are numbers, but not all numbers are scalars.
I didn't get that. All
Okay.
numbers are
So when
unscalar.
you change the coordinate, a scalar should not change. That's the definition.
Yeah.
For example,
Yeah.
temperature. If you have a temperature,
It won't change.
temperature distribution in your room, it doesn't matter which coordinate you choose, but the component of a vector, which a number, they do change.
Yeah.
So just remember one thing, that scalars are number, but that is specific kind of number. Those are geometric object as well. Geometric object means that doesn't change on the change of coordinate.
Is the definition of tensor we have learned in this session was sufficient, or there will be more rigorous?
No.
Okay.
This is the most general definition. So if you go to a mathematician, he'll give you a more sloppy definition instead.
They use a concept of abstract algebra and
they will give you a sloppy definition rather, because we were so much careful about which slot takes what. The mathematician will probably define like this. You have like consecutive m slots that takes vectors, and consecutive n slot that takes one forms. So it could be many more, like diversity could be more, but they do not consider it most time. So the definition we learned today, this is the most general definition of tensor, even more general than a mathematician. Okay, any more question? We're running out of time, so we have to stop today. But next day, next two lectures will be fun.
Bhaiya, can I talk?
Yes, sure. You can ask any question.
I missed 2 hours lecture because of the electricity problem. Could you just tell me the topics from where we studied today?
Basically, we learned the vectors and one forms and their interpretations. So it's chapter 2. You should look into section 2.5, the differential forms, and afterwards. And then we learned a small part of chapter 3, but I'm going to start from the definition of tensor again next day. So I think it will be helpful for everyone.
Okay, chapter 2.5 and onwards then. Okay, thanks.
Why 1,0 is a vector and not a one form? 1,0 tensor?
1,0 tensor is a vector because it can take a one form. So itself is a vector.
The first slot is for vector and the second slot is for one form. So 1,0 means we can take one vector and 0 one form.
No. It's the opposite. Here one means you can take one.
Okay.
Here one means one vector.
Okay.
So the first number tells how many vector it can, how many one form it can take. The second one it can tell, it tells how many one form it, how many vector it can take. So actually I made a mistake over there. That is, I should write this thing. Probably it confused you a lot, right?
Yeah.
Yeah, I get it. Yeah, I did not notice
Definition
that.
of MN tensor.
Yes. So definition of MN tensor. Did I write somewhere how many M and how many N? Okay.
You
So
told that M vectors and N one form.
no. It should be opposite. So M tensor. It should be opposite. I actually. Okay. M tensor means M type of vector character it has, N type of one form character it has. So if it has one M type of vector characteristic, then it can take M number of one form. So it can take M one forms. Oh shit. One forms. And then can take N vectors. So it has N number of vector characteristic, N number of one form characteristic. So yes, probably I was overzealous and yeah, made a mistake.
So 1, 0 tensor is a vector.
Sorry?
So the second one, as you wrote, it's the one form. It's representing this slot is representing one form. Is that this 0, 0? Then we have 1, 0 tensor. So it will be vector. You said right?
Yes. It's vector. It has one vector characteristic, so it can take one form.
One. Okay. And this will have one form characteristic. Okay. Can you please show me the last part?
Last part is this.
No, which you wrote it. Yeah, this one. Yeah.
Actually, we'll talk about it again next day because by that time you'll forget everything. Yeah, we are almost done. We'll start for more fun stuff next week. So this algebra part actually I do not like. The calculus part is more fun. Any question so far? I can allow 4 more minutes if you want.
I haven't submitted the paper yet. So is it fine to submit it today?
So there will be penalty. You can submit it today, but there will be penalty.
Penalty, okay. Actually, you said it's 7th last date is, and it's 7th today here.
Yeah, that's the due date. Oh, 7th in Bangladesh time, I said.
Okay.
It was yesterday actually.
Okay.
So yeah, if it is not over by like 12 hours, then probably penalty will be like 1 point. So it's not that much. Submit as soon as possible. I'm not going to explain. Like there is a cutoff date as well. Just be careful. Do not miss the cutoff.
What is the cutoff for every exam?
So
25.
4 days. No, 4 days. 4 days after the due date. 4 days
Well,
after the
do we need to uh, pass every exam? I
no,
mean,
no, 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 no.
oh,
You have to pass.
in
You
total.
have to pass in total.
Oh, okay, okay.
So yeah, it's
When
gonna
the
be hard.
result will be published,
No,
I asked when the result will be
oh,
published for
oh, okay.
each exam.
I cannot tell it because it's on the TS, so probably it will take 2 weeks, I believe.
Oh, okay, okay.
So the result won't be published generally. You'll see your score on Moodle.
Oh, okay. And we will have a total 2 exams before the term final.
Yes, yes. Before the final, you'll
Oh,
have 2 exams. So you just had
will
one.
they
You'll
carry
have
25% or something like that? First to
yes, yes,
25%, 25%, and then last on 50%.
50%. Yes.
Okay, thank you.
So that's why try to present something on the presentation because you could have some brownie points. So if you finally fail, then it will help. Because the first exam was super easy, but the second exam it's usually horrible. Because you have to do a lot of things. It's not hard, but you have to do a lot of work on it. Like
Then
the
I should have tried to answer all the questions. I literally just try to uh, answer what I think was enough.
no, no, no. You should try to answer as much as you can.
Yeah.
So the next exam, I can give you a hint. So the last 2 years, what I did, like I set questions for 150 points. So the like mark distribution they added up to be like around 150, and at the bottom of the paper I wrote like all the points will be scaled down to 50. So probably you'll be able to get like 100 out of it, then you'll get 33 like that.
Oh.
And that takes a lot of time because it's a lot of algebra, a lot of calculus. So yeah, that part is hard. But trust me, you'll be so much prepared for this course after this second 8 week, because this is so much crucial. This 8 week segment, this is the most crucial part of this course. Like for the preparation, like to get used to.
Yeah.
So I have another question, Deep. Like all the students which have already like done this course, what are they doing right now? Are they doing their PhDs?
No, they're actually, most of them are students. So one of them are actually doing PhD.
Okay.
So yes. Who else? Yes, so just one. Yeah.
So in your institution, like in the community of physics, is there someone who like who is like I mean to say gives matlab, I want to, if one want to do PhD, is there someone like no?
No.
Okay.
It's a small institution. We're trying to build it now, so it will take some time to go to that level. So yes, it will take some time.
No, actually, I was thinking after complete. Yeah.
We do some research, and probably that helps for many students to get into graduate school.
Okay.
So that's what we do typically.
Okay. And there was also an email about the invitation, like of contemporary. There was
Yes.
nurturing contemporary research.
Sorry.
There was also an invitation for the nurturing contemporary research. So was that compulsory to attend? I did not know about it.
You should try to attend. It's like a colloquium. So you should try to attend. And if you try to present something, as it's not mandatory for this segment, you'll get some brownie points, like you'll get some extra credit for it.
Okay. So the presentation which we have to which was optional in that lecture that was happening, right?
Yes.
Okay. So we can join it if we want to.
Yes.
Okay.
We strongly recommend.
Okay.
I think we could have joined our. There is no time left for registration, I think.
Sorry.
I think our.
I didn't get what did you?
Submitting the topic of what we want
The
to
deadline was
discuss or is over, I think.
Yes, it's over, but yeah, we started this course is supposed to be like continued every term, like every 6 months. So it's the second time we're running. So basically,
yeah.
even people at the city are not prepared for it. So what happens? They actually at the very day of their presentation, they say, "Oh no, and I didn't prepare it. Let me allow me to give me some time." So that happens. So yeah, I try to pressurize that as much as I can, but eventually it doesn't work that way. There will be someone who will be late or want to change their schedule. So okay, so far this is the 10th lecture, right? 10th session.
Yeah.
So our goal is to finish by 16th. Like we have 6 more sessions for this exterior calculus portion. Remember, it's going to be hard because it requires a lot of algebra. It's not because like it's conceptually difficult, but it requires a lot of algebra. That's why it's difficult.
Yeah.
So try to practice for this term. It will be helpful.
The Hamiltonian and Hamilton-Jacobi are just like solving differential equations.
Sorry?
Hamilton and Hamilton-Jacobi are just solving differential equations. And I didn't see any physics there.
Oh, okay. Okay. So yeah, that's a problem actually. So in elementary level, when you teach someone like oscillation for the first time, or like two-body central force for the first time, it's easy to show a lot of physics. Then actually, when we go to more abstract stuff, we do the same physics but in different way. So that sometimes helps us understanding the physics deeper, because like Hamilton-Jacobi helped us to understand, okay, there are more conserved quantity than we think. How many conserved quantities are there, that we understood. So this kind of abstract thing, they help. These are also physics, remember.
It's really interesting that how the differential equation is space or transforms actually. Like in Lagrangian, we need to solve the second order differential equations, and in Hamiltonian two first order. So it's really interesting that how it actually simplify things.
Yes, but the more important thing is about the phase space. Like that's a new space, and that has specific properties we actually did not explore much. A formal classical mechanics course would probably talk about a lot of symplectic structure or symplectic manifold. They will talk about in terms of this differential geometry. So yeah, we did not explore that much, but probably we'll have some opportunity to hear to talk about those as well, a little bit, not much, because it's not a classical mechanics course.
Okay.
Any other questions so far? I think it's already like
Just one quick question. There was no ethers theorem in the question paper. So have we done that in class?
Yes, we did.
Oh. Okay.
Any other?
That's it. Thank you.
Okay. Yes.
Thank
Okay.
you.
Thank you.
Okay. Thank you.
Thank you very
Bye.
much.
Thank you,
Thank you very
everyone.
much. Bye bye.
Thank you. Bye
Bye.
everyone.
Thank you.
Bye.